Monte Carlo simulation. Monte Carlo simulation. This is a kind of interesting part, getting a bit more interesting than the previous section. First of all, what is called Monte Carlo? Monte Carlo is a first of all, it is a place name, if you know. I put a story here already in the second paragraph. So in mathematics, today when you say Monte Carlo, basically it refers to numerical simulation of random or stochastic processes. Okay, if you want to simulate something random or stochastic, we can use computer to do some experiments. We call that simulation, and then it has a fancy name called the Monte Carlo. Okay, you can say Monte Carlo or Monte Carlo simulation or just simulation. Okay, yeah, Monte Carlo normally refer to that kind of thing. It's a computational technique that relies on repeated random sampling to obtain numerical results. The underlying concept is to use randomness to solve problems that might be deterministic in principle. Okay, so for example, in this case, we're going to evaluate the value of pi. Okay, we know the definition of pi. It is the ratio of a circle's circumference over the diameter. Okay, that's the mathematical definition. Okay, it sounds nice, but what value it is, we can numerically, computationally solve the problem. The Monte Carlo method is used a lot in applied mathematics, okay, engineering, science, too many applications. Okay, if you Google it, you can find lots of stories. A little bit of history. The Monte Carlo method was invented by John von Neumann and Stanislaw Wurman, the big names during the World War II, to improve decision making under certain conditions. It was named after a well-known casino in Monaco. You know, a very small country near France. They have a famous. It's famous for many things like the casinos and the F1. I think they have F1 event there every year. Okay, some story in history, if you can read, just have a Google. Because probability and random modeling is historically related to gambling, also today related to gambling. So Monte Carlo is used by somebody to name this method. Okay, so we're going to use today's computer to process random numbers. Okay, and then to simulate the probability system. Okay, today is much easier than before because the computer is faster. The computer is much faster today. All right, let's do it. Okay, so question is, what is the value of pi? We know the definition of pi is the circumference over the diameter, as indicated by this graph. Okay, and how to do the problem? How to solve the problem? We're going to use the Monte Carlo method. All right. What's the logic of thinking? Now, if I tell you the diameter or radius of a circle, okay, then we know that if I tell you the radius or diameter of a circle, then we can calculate the circumference, okay, and the area of that circle, okay. So for example, here we have a circle. The diameter is 2. In other words, the radius is 1. The radius is 1, okay, in this diagram. And then we know that the area of the circle with the radius of 1 will be pi radius squared. So if the radius 1, then the area of the circle will be pi, right? Because the radius 1. And then if I draw a square around the circle like this, then the size, one side of the square will be the radius, which is 2. Then the area of the square will be 2 squared, will be 4. Right? Yeah. Now, if I use computer, to generate random points within this square, okay, just randomly generate points within this square. And then I can calculate something. I can calculate how many points are falling in this circle. Well, all points will be in the square, but I can calculate how many points are falling in this circle. Okay. And then if I divide the number of points in the circle over the number of points in the whole square, that will be the size of the circle divided by the size of the square. Okay. Right. I know the size of the circle is pi, which is but the value I know it's just the pi, just a symbol, but the value of the area is 4. So in this equation here, in using computer simulation, we can generate a large number of points in the square, so we don't have the denominator here, and then we can count how many points are falling in the circle, which is the numerator. And then I know the whole right-hand side. I can calculate this number. That number will be equal to the value of pi. Okay, that's the thinking of this experiment. Okay, and you can imagine the more numbers, the more points we simulate, the more precise the value of the pi we can approach. Okay, if you only generate 10 random points, the evaluation of pi will be very far away from the true value. But if you generate 10,000 or 1,000 points, that will probably fill the whole area, the square, and then do the calculation here. I can see we'll probably precise approach the true pi value very closely. Okay. And by the way, at the bottom left corner, if you want to know, okay, why the area of the circle is pi r squared, that is little proof. Okay, you can think of we are cutting this whole circle, not circle, the whole disk into many circles. The larger one, smaller one, smaller one. And then each of them, each tiny circle, the circumference is pi to the radius times pi. Okay, and then if we cut them off and then put them this way, you will form a triangle. Okay, the bottom will be the 2 pi r, the largest circle in the edge, and then the top bit will be the smallest circle in the center. Okay, and then the height will be basically the radius of the original circle. And then we know how to calculate the size of the triangle. That is 2 pi r times r divided by 2. And then you get pi r squared. Okay, it's one way to prove that the area of a circle is pi r squared. Okay, yeah, if you're interested in that. All right, okay, let's do the simulation now. So first of all, I'm going to decide how many random points I'm going to draw or simulate in this session. I call this number points, NUM points. Let's say I want to draw 1,000 random points. And then I'm going to create another object called a random number points in circle. Current initial value will be 0. Okay, initially nothing in the circle because we haven't really started calculating yet. Let's do this. All right, I just created 2 objects. Number of circles, the number of points, 1,000, and the number of points in circle, initially 0. Okay, and then I'm going to set a random seed. You probably will see this one a lot if you read something about Monte Carlo method, because we are using random simulation in computer. Computer will use random numbers or pseudo random numbers. If we don't decide the random seed, every time you run the code, you probably get different results. And then if you share the code among your friends, different people may get different results because the results is totally random. But if I set the random seed, and then the randomization will starting from this seed. And then every time you run the same code with the same random seed, the results will be the same. Okay. And if you share the code with other friends, if they all use the same random seed number, and then the results will be also the same. So we call that random simulation, but actually it's not 100% random, to be honest, because it's all the random numbers are generated according to some algorithm. So as long as this algorithm is not 100% random, we call them pseudo-random numbers. Okay, so what's the seed for the pseudo-random procedure? We can nominate it. So here I'm going to use 1, 2, 3 as a random seed number. You can use whatever number you like. You can use 1, 2, 3, 3 to 1, 100, 1,000, 500, 1 million, doesn't matter. Okay, so I'm just using 1, 2, 3 here to set the random seed of my code. So if I run again tomorrow, or if I share with my friends, if we use the same random seed 1, 2, 3, we should get the same results. So now I'm going to use coding. Remember last workshop, we learned something like a looping. Here we're going to use a for loop. Okay, use a for loop. For each single object in a sequence from 1 to 1,000, this number of points 1,000. Okay, you can see I'm going to loop the thing 1,000 times from 1 to 1,000. I'm going to use a RUnif F. That is the R function of uniform distribution. If I go back to the list, I have a uniform distribution, P uniform, Q uniform, D uniform, R uniform. So in this case, I'm going to use R uniform. I'm going to use the RUnif function to generate random realizations of a uniform distribution. A uniform distribution must be a continuous distribution within some range. So here, my uniform distribution is between -1 to +1. Actually, I'm using two uniform distributions. So I'm using the uniform distribution twice. The first time, I'm going to generate the x coordinate of a point between -1 and +1. And then I'm going to use the same uniform distribution to generate a y coordinate randomly between -1 and +1. Okay, so this uniform distribution is a distribution between -1 and +1. If you draw the curve of a uniform distribution, it's just a flat line. That means within this domain, possible values from -1 to +1, the chance of seeing each value is the same. Okay, it's equal to see any value between +1 and -1. Okay, so I'm just using R uniform to generate the x and y coordinates of a random point within -1 and +1. Okay, and then I check if this point is within the circle or not. I just calculate the distance from that point to the center. The center is 0. Remember, the center of the circle is 0. Or the center of the square is also same center as 0. Okay, so if the distance from the origin, the center to the point is less than 1, I say this point is in the circle or on the circle. Otherwise, it's not in the circle. Okay, so if the distance is equal less than 1, I count this point as in the circle. So this my count of the number of points in circle will increase by 1. Otherwise, we don't do anything. So if the distance is between the point to the origin is larger than 1, I'm not counting. I'm not increasing this number of points in circles. Okay. All right. So I run this. I generate 1,000 random points using the for loop from 1 to 1,000. For every generation of points, I do the same thing. Okay, you can see some points will be counted as in the circle, and some points will be not counted as in the circle. And after the whole looping, I can print out the ratio using this formula here. The ratio of points in the circle over the points in the whole area times 4. Okay, this formula comes from Harvard setup of the experiment here. That number will be our evaluation of the pi value. Okay, so let's do this. Let's do this now. Let's see if we get a 3.14 something. Okay, run. Very quick. Our evaluation is 3.028. All right, not too bad. It's a 3 point something. It's quite close to the. We know the true pi value is 3.1415926. Blah 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 blah. Okay, so it's not too bad. It's just a little bit off the target, but not too bad. All right. If you're using different random seed, you make a different number, different result. Okay. And if I increase the I can imagine if I increase the number of random points, I will see the results more kind of closer to the true value of 3.14. So let's do that. So I'm going to write a function in R for this simulation of pi. All right, so you can say I'm going to name my function called the Monte Carlo pi, Monte underscore Carlo underscore pi, and it's going to be a function. And then I need two inputs: the number of points I also want to set up the seed as an input. Okay. If you have any questions, just yell out. Yeah, no problem. No problem. If you want to leave, it's okay. Make sure you download a copy of the slides and then give a try at home. And I will share the recording next week, I think. All right. And then in this function, initially, again, I'm going to set a number of circles. In circle is 0, and then I will take the random seed from the input. Okay, if I put the 1, 2, 3 here, random seed will be 1, 2, 3. And then I'm going to use the for loop from 1 to number point you input in the function. And then again, for each round of looping, I'm going to create a random point between -1 and +1 using the uniform function, the R uniform function, the X coordinate, Y coordinate, and then I'm going to calculate if the point is within the circle. If it is, point in circle will increase by 1. And then I will return the pi valuation of this simulation. Okay, basically I just wrapped the original code in the previous slide, wrap it into a function called the Monte Carlo pi. And then I can, once I have the function, I can use the function to run multiple experiments, to run a series of experiments. Each time we're going to use a different number of points. We try from 10 points, 100 points, 1,000 points, 10,000 points, 1 million points. And then each experiment, we will get a pi value estimation or evaluation, and then we're going to plot the pi value evaluation, against the number of runs in each experiment. And that I should expect to say something like this. So as I increase number of points in the experiment, the evaluation of pi will approximate 3.14. That is the true value. Right? Let's do this. If you came to my last workshop about basic programming in R, we did something similar. Remember, we did we used the recursive function. We wrote a recursive function to evaluate the Fibonacci sequence of numbers, and then we calculate the ratio of the last two numbers of Fibonacci sequence. As we saw before, as we increase the number of Fibonacci numbers in the sequence, the ratio will approximate the golden ratio, 1.618. Okay, yeah, we'll do something similar here too. So we're going to first of all define this function, Monte Carlo pi. I'm going to define this function. So you will see you will see a new object here as function. Okay, let's highlight this function and then run it. I have a new object with a Monte Carlo pi function here. Okay, and then I'm going to use the function multiple times. So I'm going to run the experiment 100 times. Okay, so first of all, the first time I will evaluate. In the first experiment, I will generate 100 points and then evaluate the pi, and then I increase the number of points by 100 each time until I reach 10,000 points in the final experiment. So 100, 200, 300, 400, 500, 1,000, blah, 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 until 1,000, 10,000. So I'm going to, first of all, generate a sequence from 100 to 10,000 by 100. So it will be 100, 200, 300, 400, blah, 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 until 100, about 10,000. Okay, and then I'm going to create a vector called pi. I will fill up the vector of the evaluations of pi in each of the 100 experiments later. Okay. Okay. And then that is the code to do the experiment, just only here. Okay. So now I have we have a sequence here. It's from 100 to 10,000 by 100 each time. So basically, I'm going to do a for loop again. Doing a for loop. So for each number of points in this sequence, from 1 to 10,000 in this case, the length of this sequence, the length of the sequence is 100 because we have 100 experiments from 100 to 10,000. So from the first one, the last one in this sequence, for each number of points, I'm going to calculate. I'm going to use the Monte Carlo pi function to calculate a value of pi. Remember the Monte Carlo pi function is only the two inputs, the number of points and the seed. So the number of points will be the element of the sequence. The first one will be 100, second one will be 200, 300, and all the way up to 1000. And the number of the random number seed is 1, 2, 3. I use the same one. Okay. Okay. So basically, I'm going to run the experiments 100 times. Each time we have a number of points in this sequence, 100, 200, 300, all the way up to 10,000. And then for each time, I'm going to use the Monte Carlo pi function to evaluate the pi value. And then I put that into this vector pi, appended in the pi vector. Okay. So after this series of 100 experiments, I'm going to put these two vectors into a data frame. Okay, into a data frame. The first vector is number of points of each experiment. The second vector is the pi value from each experiment. And then once got the data frame, we can just draw this graph as we did in last week, which is a line chart or run chart. Okay. All right, let's do it. First of all, define these two vectors. Okay. The first one sequence, and then we run the experiment here. This will take a file. It's calculating now. Done. Okay. It's done. And then if I want to have a look at pi, this vector, that is the pi values we evaluated. There are 100 pi values because we had 100 experiments run already. Yeah. And then we're going to create a data frame. We call this one results. Just combine the two vectors, or the sequence and the vector, into a data frame. We call this one results. Have a look. That's the results data frame. Number of points in experiment, and then the experiment result of evaluating pi. So we have 100 experiments here. Okay. Okay, given this data set, we can easily plot the chart here, the run line chart. Here's a reference line of the true pi value. Control V. I don't think I need to load the ggplot again because I just loaded it before. So just run this charting code directly. So the geom line, this dataset name results. X-axis is number, Y-axis is pi. We have a geom line and we have a reference line that is the true value of pi is a 3.151415926 blah blah blah. It's just up to this point, and this dashed line is red, and then background is black and white, and like this. Okay, we got the chart here. We got the chart. So as you can see, when the number of points is 100, that's the first one. Our evaluation of pi is a very off the target. It's 3.4. And then as I increase the number of points in each experiment, we are approaching the true value of pi. Sometimes higher, sometimes lower. But you can see up to, so when we have like a 7,000 or 8,000 points, the value is kind of stable around 3.14. The last one is when we have a 10,000 points in experiment. It's pretty close to 3.14. Okay. The raw results is here. Okay. Yeah. So that's it. That's the Monte Carlo simulation for evaluating pi using the random functions. We use the R uniform function basically here to generate the random points within the square. Basically, we use the R uniform function to generate the value of the x and y axis of a point within this square. Okay. It's kind of interesting exercise. Okay, we know we use a uniform function, we use a randomization function. We also use some looping coding in the previous week we learned. Yeah. Any questions about this part? Monte Carlo pi, that's how I use my, because I remember here I define this Monte Carlo pi as a function, my homemade function, handmade function, and then I'm using the function here. Remember in the Monte Carlo pi function, you have to give two inputs, the number of points you want to simulate in this round of experiment, and the seed of the random number. So here, every time I'm using the same random number, same random seed, 1, 2, 3. And then the number of points comes from the sequence I set up initially. This sequence is like from 100 to 10,000 by 100. So there are 100 points in this sequence. 100, 200, 300, 400, 500, 600, 700, 900, 1,000, 1,100, 1,200, all the way up to 10,000. So there are 100 elements in that sequence. So I'm looping in the sequence from the first one, 100, until the last one, 10,000. The length of this sequence is 100 points, right? 100 elements. Yeah. So the length of the sequence num is 100. Yeah. So we have 100 elements. Basically, we run a series of 100 experiments. In each experiment or in each Monte Carlo, we have different numbers of points we randomly generated. Okay, in the first experiment, we randomly generated 100 points. In the second experiment, we randomly generated 200 points. Keep and on and on and on. In the last experiment, we randomly generated 10,000 points. Okay, so in each experiment, we use random points to evaluate the pi value. So we have a 100 pi evaluations. Okay, you can see initially it's very inaccurate, but as we increase the points in the experiment, the evaluation of pi is getting closer and closer to the true value, 3.1415926. Yeah, the num_j, that is to, if you came to the workshop last time, num is a sequence. You can also think of as a vector. It's a bunch of elements in an array. We can use a square bracket and a number to refer to the every single element in the vector or sequence. So you say j is from 1 to 100. So if in the first round of the looping, for looping, num1, that will refer to the first value in the sequence, that's 100. And then num2 in the second round, that will refer to the second value in the sequence, that will be 200. The last round of experiment will be num100. That's the length of the sequence. Num100 will be 10,000. So in the last round of experiment, we will use the Monte Carlo pi function to generate 10,000 points. Okay, and then you can imagine if I fill 10,000 points in the little square from -1 to +1, -1 to +1, x and y, it will be very dense. It's almost filled. Okay, almost filled. And then the ratio, evaluation of pi using this ratio will be very close to the true value. Yeah. The reason I put a seed here is just for people. The reason I put a random number seed here as an input of the Monte Carlo function is just for you to, like, if you want to share your code with other people, or if you run the code multiple times. If I don't set the seed, the results will be different from person to person or from session to session. But if I set the random number seed to be the same value every time, then you should get the same graph, same results from person to person, from session to session. Yeah, because in nature it's not truly random; it's a pseudo-random, because the random numbers are generated here, ram-nif. The randomization is based on the algorithm in the R language, but it's random enough, not 100% purely random, but random enough. Okay, any other questions before we move to the next round? The final round. Now the final exercise, let's see if we have time to cover all of them. I think we probably should. So first of all, if you haven't learned this one, I think you probably should. I don't know. You know, the real power of statistics is in statistical inference. So basically, we can infer on a random variable's population parameter based on the statistics you observe in a random sample. So for example, everyone starts learning this statistical inference from the first concept, the sampling distribution of sample mean, or sampling distribution of the mean. The mean means the sample mean, or SDM. We know that if the sampling is random, okay, then the SDM, the sampling distribution of the sample mean, will have the same mean as the population mean. And the variance of the SDM, the variance of the sample means will be equal to the population variance divided by sample size. Okay, and more importantly, but more interestingly, the sample means will follow a normal distribution. Or the sample means will approximate a normal distribution as we increase the sample size. Okay, that's central limit theorem. So in other words, if the original distribution is not normal, if the original distribution is normal, then the central limit theorem doesn't really matter, because if the parent distribution is normal, then the distribution of the sample mean will always be exactly normal. But the true power of central limit theorem is if the original distribution is not normal, okay, if the parent distribution is not normal with a finite mean of variance, the shape of the SDM, the shape of the sampling distribution of the mean, will become very normal if the sample size is large enough. Okay, yeah. So that's the content of central limit theorem. That's a real power of kind of magical, because once we know the distribution's mean and the variance, we know everything about this distribution, as long as the distribution is normal. So now it tells us, according to central limit theorem, we don't have to worry about the original distribution's shape. So as long as our sample size is large enough, then we can assume that the sampling distribution of sample mean will be very close to a normal distribution. Okay, and then using this property, we can do many things, including statistical inference and lots of statistical tests and estimation, hypothesis testing. Okay, those kind of stuff. So let's verify. Not today. I just want to verify the central limit theorem. Okay, the central limit theorem is derived mathematically, analytically, using the formulas. We don't have time to show that, it's a bit complicated, but we can computationally verify it. Okay, we're not going to prove that mathematically. We're going to just see it. Okay, so we're just going to, okay, let's define a non-normally distributed distribution. Let's say a Poisson distribution is not normal. Okay, and then let's draw multiple samples that simulate the sampling distribution of the mean. So let's draw a large number of samples from this Poisson distribution, which is not normal. And then in each of the sample, we're going to calculate the sample mean. And then we're going to observe the distribution of the samples is sample mean. So if it looks normal, and then we can again do the experiment. So we can do the experiment multiple times. So first by using different number of sample size. So let's say initially we draw, let's say five observations in the sample, and then we draw like 10,000 samples, and then we see the distribution of sample means of the 10,000 samples. They all have the same sample size, 4 or 5, and then we increase sample size to 10, and again we draw 10,000 samples. Each has 10 observations, and then we calculate the means, and then we plot their means using histogram, and we see if it's normal or not. And then we see increase our sample size to 20, 30, or 50. Okay, so every time we use a larger sample size, and then we simulate the sampling distribution of sample mean, and then we see the distribution of sample mean. Let's see if it's approximating a normal distribution as we increase sample size each time. Okay, yeah. So what is a Poisson distribution? I put something here. You have a read if you have time. So Poisson distribution is a discrete. It's not even continuous. It's a discrete. Okay, it's even more interesting. It's discrete. that can predict a number of events given some space and time, whatever. We use this one to simulate a random occurrence of things a lot in science, engineering, and management. Okay, that is the probability mass function of a Poisson distribution. It involves factorial, exponential, Euler's number, but don't worry, you don't have to calculate anything. Computer will manage everything for us. But we have to know that Poisson distribution is discrete. That's the probability mass function. So given a number, given a random number's value, we can calculate the probability using the Poisson probability mass function. So this one will always return some value between 0 and 1. Poisson distribution is only defined by one parameter called lambda. The lambda is the average rate of occurrence. Here, I put it here. Average rate of occurrence. The lambda has to be larger than 1. No, sorry, larger than 0, larger than 0, larger than 0. And then the Poisson distribution only depends on this one parameter. And then for any Poisson distribution, the mean and the variance is equal to lambda. Okay. Then there's something you have to know that when the lambda is small, the Poisson distribution is highly skewed to the right. But if I increase the lambda, the shape of Poisson distribution will become more and more like a normal distribution. Okay, yeah, it's just something because Poisson distribution, normal distribution, they all belong to the same family of random distributions. Okay, but there's something about probability theory we don't want. No, we don't have to talk about that. So let's do the simulation now. So this one. What did I do? Okay, this one. Now let's see. This is the steps for the simulation. So randomly draw a small sample. Let's say sample size 4 from a positive skewed Poisson distribution. Let's say the Poisson distribution lambda is 1. It's highly skewed to the right. And then calculate the sample mean. And then repeat the step 1 number, step 2 multiple times. Let's see 10,000 times. So we're going to draw 10,000 samples from a Poisson distribution with lambda equal to 1. Okay, and then for each of the 10,000 samples, they have the same sample size, which is 4. And then for each of the 10,000 samples, we're going to calculate the sample mean. And then we'll plot the 10,000 sample means in a histogram. And we're also going to calculate the mean of the means and the standard deviation of the means. Okay. That's the first round of experiment with sample size equal to 4. And then, as you can imagine, the distribution of the sample means will be won't be very normal. It probably skewed to the right as well. And then we increase the sample size to 36. Okay, so every time we draw a sample of 36 observations, and then we draw 10,000 samples from the Poisson distribution with lambda equal to 1. And then we plot the histogram and then see how it looks. I can tell you when the sample size larger, 36, the distribution of the sample means will look very, very normal. Okay. All right. So let's copy the code, see what happens. First of all, I set the seed to be 45, and then lambda is 1, and then n is 4, sample size 4, and then I request 10,000 samples. Okay, run this. Bunch of objects. So So we will draw 10,000 samples. Each sample has 4 observations. So basically, we have to draw 4 times 10, 40,000. 4 times 10,000, 40,000 observations from the Poisson distribution. Okay, so that's what I do here. We use R plus POIS. That's the R function of Poisson distribution. So the lambda is defined, which is 1, and we're going to draw 40,000 random numbers from the Poisson distribution. The 40,000 comes from 4 observations per sample times 10,000 samples. All right, SIM. Yeah, see, we have an object here called the SIM. It has is a vector of 40,000 elements. Okay, all from the randomly draw from the Poisson distribution with lambda of 1 using the R plus function. Okay, and then I'm going to put this 40,000 draws into a matrix with 10,000 10,000 rows to represent the 10,000 random samples. All right. Each sample has 4 observations. Can use this one. There's something new here. This one. Okay, I'm going to put this vector into a matrix. Number of rows is m. M is the number of 10,000 samples. Okay, this is a matrix function which is a little bit new, but nothing, not difficult to understand. So X is a matrix now. It looks like data set. Okay, we can double click, see what it looks like. Like here. We have 10,000 samples, and each sample has 4 values, 4 random draws. So in total, 40,000 random draws. Okay, it's a matrix. We call this X. And then what do? We need to calculate the sample means, right? Because we are interested in the 10,000 samples is sample means. So we're going to have use the row means function of the matrix to calculate the means and then put them into a object called sample.means. Sample.means now is a vector, has a 10,000 means from the 10,000 rows or 10,000 samples, right? And now we can calculate the average of and the standard deviation of the means of the means. So we can calculate the mean average of the means and the standard deviation of the means. The average of the means is 0.999. Theoretically, it should be equal to 1 because remember, for Poisson distribution, the mean is equal to variance equal to lambda. Our lambda is 1. So ideally, the sampling distribution, the mean should be equal to the original mean, which is lambda, which is 1. Okay, and the variance should be what? What should the variance be? The variance should be the population variance divided by the sample size. So our population variance is lambda, which is 1. Sample size is 4. So the sampling distribution's variance should be 0.25, right? And the standard deviation should be 0.5. Again, our simulation is almost the same as a theoretical value. the standard deviation of the sampling distribution's mean is 0.5, 0.4, 0.540. So you can see our simulation did a quite good job. Okay. And then let's plot the histogram of the 10,000 sample seed means with a red density curve, again, of the means, and then a blue theoretical normal curve of a normal distribution with a mean equal to lambda and the standard deviation of the lambda divided by the sample size and taking square root. Why it is this? The answer is actually the answer of the yellow part is actually given to you here. Central limit theorem here, right? This second point. The variance of the standard deviation of the sampling distribution of the mean is equal to population standard deviation divided by the square root of mean sample size. Okay, yeah. So that's what we do here. So we're going to plot the data sample means at the data frame. The x is a, because we are plotting a histogram, the x is the variable sample dot means. And then we have a histogram of density and the density plot. And also use a step function to plot the true or theoretical density curve of a normal distribution, d norm, with a mean equal to lambda and the standard deviation of lambda over n square root, and the color is blue. Okay, and then we say this is simulated sample means is n equal to 4. Here we go. We got this one. We got this one. So that is the looks a bit funny, right? Because remember, Poisson distribution is a discrete in nature. So we got the 10,000 samples, and then we plot their sample means. That's the histogram of the sample 10,000 samples. Is sample means. Obviously, it's not looking very normal. It's kind of skewed to the right. Okay, and then we have gaps because the original distribution is normal. Is discrete. Okay, and then the theoretical normal curve is blue, and the empirical density curve is red. It looks not too bad, but not too good either, right? I have the graph on the second page here. You see. So with such a small sample size, the sampling distribution of the mean based on a positive skewed Poisson distribution is still skewed to the right. Okay, now let's increase our sample size to 36. The only we just repeat the same thing. The only difference here is the sample size of each sample now is not 4, it's 36 now. Okay, I mean everything else is the same. And if you do that, you should get a graph like this. And you can see the red density curve, which is of the data, and the blue density curve, which is from the theoretical normal distribution, they almost the same, kind of overlap each other. That means now with a larger sample size, the sampling distribution of sample mean is very, very close to a normal distribution. So we just verify the sample central limit theorem. So again, any questions? And before you go,